So here you see in this table, in the outline, I've posted a number of the common elements that we're going to discuss in this class. And as I said, you can see those with two letters in the symbol always have a capital letter and followed by a lowercase letter. So it's always going to be that way when you're writing chemical formulas. And as I mentioned before, the elements and atoms actually come in different flavors, and we call those isotopes. So the word iso means the same. So isotopes are just different masses of atoms, but they're the same element. So we need a way to distinguish between different isotopes. The symbol for a specific isotope of any element is written by placing the mass number as a superscript. This is how we're going to distinguish different isotopes symbolically. So you place the mass number as a superscript to the left of the element symbol. The atomic number, which is the number of protons, is sometimes written as a subscript to the left of the element symbol, but it won't always be written as a subscript over here because the symbol itself, in this case magnesium, is sufficient to tell you that the atomic number is whatever. You don't necessarily need that subscript right there, but it'll be, if it's there, it's fine. If it isn't, it's fine as well. So for example, you have magnesium 24, what we call magnesium 25, and magnesium 26. And almost every element in the periodic table has a mixture of isotopes. There are a few that don't, and I'll point those out to you. All isotopes of magnesium have 12 protons, but the number of neutrons are different. These isotopes have, respectively, this one has 12 neutrons, this one has 13, and this one has 14. And so it's very easy to figure that out. You just take the implied atomic number, which is 12 in this case, and subtract it from the mass number. So 24 minus 12 is 12, 25 minus 12 is 13, and 26 minus 12 is 14. So these are all magnesium atoms, and they behave chemically as magnesium, but they have different masses. For instance, you can even have, or actually what I was talking about earlier, when you have ionic symbols, you just have to remember to add the ionic charge to the symbol. So again, the mass number is a superscript. That's the sum of the protons and neutrons. The atomic number is the subscript, often omitted. That's the number of protons. And the charge is often written as a superscript to the right. Hydrogen, the most common element, has 3 common isotopes. Now, if you look up on Wikipedia, you might see more elements or more isotopes than this for any particular element that I might talk about. What I'm giving you in these lecture videos is just the common isotopes. And oftentimes, for more common elements like this, the different isotopes have unique names. The one with a mass number of 1 is called protium. This one with the mass number of 2 is called deuterium, and this one is called tritium. The prefix tri means 3. And this one, the tritium, is radioactive. I believe tritium is actually a byproduct of nuclear power plants in the cooling water that they use to cool the control rods. So they have to be very careful in how they dispose of the nuclear waste and treat that water. Hydrogen 1 is 99.989% abundant. So that means the vast majority of hydrogen that's floating around out there in the universe is mostly this isotope. Hydrogen 2 is about 0.0115 abundant, and hydrogen 3 is trace. What trace means, it's at a very, very low level. It's much less than hydrogen 2 in this case. If you had to make an estimate, it's probably much less than, let's say, 0.001%. It's almost undetectable except with extremely sensitive instruments. More isotopes, let's see, we talk about carbon a lot in this class, so the 3 common isotopes of carbon are what we call carbon 12, There's also carbon-13, and there's also carbon-14. And another way to write these names, I'll put it in quotes, is we'd call this one carbon-12 with carbon-12. This one we'd call carbon-13. And of course we'd call this one carbon-14. And this one, carbon-14, is actually the radioactive flavor, so to speak, of carbon. And they use carbon-14 in what's called carbon-14 dating. So when they date fossils and dinosaur bones and things like that, they actually use carbon-14 dating, which means that every living thing has some level of carbon-14 in the tissues, in the bones, and the whatever. So this gives off radiation. I think it's, I'm not sure if it's alpha or beta radiation. But the point is that they know the half-life of the radioactive isotope. It's a little over 5,000 years. So by measuring the amount of radiation coming off of a bone that they find or a tissue or whatever, they can actually tell how old it is, because they know in a living being the amount of carbon-14 is always constant. And so as soon as a organism dies, it's the amount of carbon-14 that it takes in stops, and it whatever was left when it died starts to slowly decay. And so they can tell by how much carbon-14 radiation is coming out of that. They can tell how old the object is, and it's pretty accurate. The one common element we'll talk about a lot in this class that just happens to have no other isotopes is fluorine. It exists wherever you look for it or find it in compounds. It always is fluorine-19. So what I'm getting at here is that when I say carbon, I'm usually mean carbon-12, but the carbon that you see, the symbol that you see in the periodic table, is actually a weighted average of all the common isotopes. The mass that you see is the weighted average of all three of those. So how do we calculate the atomic mass, or the mass of an atom? So remember that each proton and each neutron has a mass of about 1 atomic mass unit. Each electron weighs a lot less, so we essentially ignore the mass of the electron. So the atomic mass of a single atom in atomic mass units is approximately equal to its mass number, the sum of protons and neutrons. But again, most elements exist naturally as a mixture of two or more isotopes. So different isotopes have different masses, and the periodic table lists what I had said. Lists the weighted average mass of all the isotopes present in a naturally occurring sample of that element. So, as I said, wherever you find carbon out there in nature, whether it's in a living organism or it's in gasoline, there's always going to be the same proportion of carbon-12 to carbon-13 to carbon-14. And that's because the universe is so old, all the atoms have kind of equally distributed themselves among all known everything, among all matter, whether it's living or non-living. So let's do a few examples and show you how we can do this. It's pretty straightforward. So the average mass, just in general, is the sum of each isotope mass times the percent abundance of each isotope. The percent abundance of each isotope is something you would have to determine experimentally from using an instrument like I showed you. Kind of looks like you'd get traces like this on a computer screen. You would get peaks that are proportional to how much of an isotope is present. So for example, the element boron is composed of two main isotopes. We know 19.9% of naturally occurring boron is boron-10, with a mass of 10.0129 atomic mass units, and 80.1% of boron, naturally occurring boron, is the isotope boron 11 with a mass a little bit more than 11. Remember, this boron 11 actually weighs a little more than 11, just like boron 10 has a mass a little bit more than 10, because the mass of protons and neutrons, each proton and neutron has a mass slightly greater than 1 atomic mass unit. So the average mass that you're going to see in a periodic table is calculated this way. You take the percent abundance of a particular isotope and convert it to decimal form. So 0.199 would, 19.9% would be 0.199, and you multiply it by the atomic mass in atomic mass units, and you add to it the percent abundance of the other main isotope. So that would be 81.1% in decimal form is 0.801, and then you multiply it by the mass of that isotope in atomic mass units, and you would get, this number is 1.9, I wouldn't round off yet, 1.9925671, and you add to it this number here, which is 8.8184493, and you get, when you round off to 2 decimal places, 10.81 atomic mass units. And look in a periodic table, you'll see that the mass of a boron atom is 10.81 atomic mass units. And that's how it's done. And you can do that for 2 isotopes or 100 isotopes. It doesn't matter. It's I'm going to give you a different way to look at it, just to make sure you have that concept understood. The occurrence and natural abundances of isotopes can be experimentally determined, as I said, using this mass spectrometer. Almost every lab in the world has one of these, and the symbol, they use this acronym capital M, capital S, or GCMS, which stands for gas chromatography mass spectrometry. We have these instruments on the 4th floor of Halsey on the Oshkosh campus, and we use them all the time for analyzing materials. What happens in this instrument is the sample's vaporized. You inject it with a syringe into a very high temperature tube, and all the compounds are turned into gas, and then they get zapped with a beam of electrons, and which knocks other electrons off the molecule and breaks the molecule into pieces. It basically shoots bullets of electrons at it, and it breaks into pieces, and we can tell based on the pieces that come out, and we can kind of piece the molecule back together. It's pretty standard procedure. These cations are then separated by their mass and charge. So as the molecule is bombarded with these high energy electrons, it falls apart into different pieces, and you get this is a very simplified version of it, but you get a chart. The more isotopes that are coming off through the instrument, the higher the peak is. So this evidently is zirconium, and it has a mixture of isotopes: zirconium 90, zirconium 91, zirconium 92, 94, 96. It's got 5 different isotopes that the instrument is detecting, and then the percent relative abundance is just on the y-axis. And so you can just apply that formula I just showed you for an element like this. I'm assuming this ZR is zirconium. But this, again, this diagram's kind of small. I've shrunk them down on the outline. But again, it works like this. You inject your sample into the mass spectrometer. It is a beam of electrons hits the vaporized sample, knocks an electron off, and then the molecule is very unstable at that point, so it flies apart into different pieces, and the ions that come out, which are positive charges, are accelerated through an electric field, and then they pass through a magnetic field, and based on how massive they are, they might bend at different angles. So you can actually, the detector's kind of at the end of the tube, this tube, and they're focused on different parts of the detector by varying the strength of the magnetic field. So you can actually kind of scan through the different masses and focus the heavier ones on the detector and then scan by changing the magnetic field a little bit and pick up the lighter or the heavier isotopes. And that's how a mass spectrometer, or spectrum, we call it a mass spectrum, is generated. Now, another way to look at how you can, what I'm talking about with the atomic mass of an element, like I showed you here for boron, is this way. So let's talk about chlorine. We can calculate the atomic weight, I'll call it, or atomic mass of an element. I'll often use those terms interchangeably, atomic weight and atomic mass. Atomic mass is more correct. But anyway, you can calculate it from the individual masses of the naturally occurring isotope. So for instance, I show you here how I calculate, or how we calculate the atomic mass of chlorine, naturally occurring chlorine. So we know from using an instrument like a mass spectrometer is that 75.77% of all naturally occurring chlorine, I should really use capital C, lowercase l, but that's not important at this time. About 3/4 of naturally occurring chlorine is chlorine 35 with a mass 34.97. And about 1/4 of naturally occurring chlorine is chlorine 37, 2 atomic mass units, about 2 atomic mass units heavier. So what is the mass we should report in the periodic table? Because again, no matter where we look on Earth or out in any other place in the universe, we'll always find this percent ratio of chlorine atoms. Out of every 4 chlorine atoms, about 3 of them will be chlorine 35 with this mass, and about 1 out of every 4 chlorine atoms will be this one with 2 more neutrons, so it's heavier by 2 atomic mass units. But the calculation is the same as I showed you with boron. You take the percent in decimal form of each isotope and add them together, and you get 35.45 to 2 decimal places, and that's what you'll see in the periodic table under chlorine. We're eventually going to think of atomic mass units as grams, but we'll talk about that in the next few videos. So it's the same thing. A practical example that might help solidify this concept is if we calculate the average of a series of exams. We're kind of doing the same thing. Suppose you have 2 scores of 80 and 2 scores of 88 on 4 exams, and it's out of 100. So if you just average those numbers, 80 plus 80 plus 88 plus 88, and divide by 4, you get 84 for the average of those 4 scores. It's the same thing. What I'm doing with the atomic mass is the same thing I could do with these scores. 50% of my scores are 80, 2 out of 4, and 50% of my scores are 88, so half are 88. So half of 80 is 40, half of 88 is 44. You add them up, you get 84. Of course, you get the same answer. It's just a different way of looking at the average. And that's exactly what we're doing when we calculate the weighted average of any of the elements or atoms in the periodic table. So I want to just add to that video another way to look at percent abundance of isotopes. So recall that a mass spectrometer detects different isotopes as they come through the machine based on how it varies that magnetic field that the cations, the positive charges, are passing through, and it gives us the percent abundance of each isotope. So let's look at carbon again. Now, carbon-12 is by far the most common isotope of naturally occurring carbon, 98.9%. Carbon-13 occurs at about 1.1% naturally, and carbon-14 is very, very rare, less than 0.0001%. Well, I wanted to put that into actual numbers for you, so I did a little arithmetic, and I found that if I convert everything, if I assume that I have 1 trillion carbon atoms, which sounds like a lot, but on atomic level, or when you measure in a laboratory, even trace amounts, you're talking about far more atoms than 1 trillion. So this is what you would get. You would get, out of every trillion carbon atoms, 989 billion of them are carbon-12, based on that percent. 10,999,999,999 coming through the machine would be carbon-13, and every once in a while, out of every trillion atoms coming through the mass spectrometer, only one out of a trillion would be a carbon-14 atom. And so that is very rare. But remember, that's enough. 1 out of a trillion is enough for our instruments to pick up its radioactivity, so we can actually do carbon-14 dating of fossils.